Let's listen to the supplemental problem 317. You can find this problem in the ECE302 ebook in the Chapter 3 supplemental problems starting on page 23. Given this PNP transistor circuit, if beta F is 50 and the emitter base turn-on voltage is 0.6 and the emitter collector saturation voltage is 0.2, can you find the base current, the collector current, and the emitter collector voltage if this resistor is 43K or 3.3K? And then could you figure out the value of this that would put you at the edge of saturation? I have quite a few loops here to analyze. I could simplify this by taking this part of the circuit and Thevenizing it and putting it back. I've got a 10-volt battery back to ground, a 36K and a 68K hooked up between the base and ground. We'll disconnect that. This is the open circuit voltage, which is also the Thevenin voltage. So that's going to be a voltage divider of 10 volts times 68K over 68K plus 36K, and that's 6.54 volts. If I set all the independent sources equal to 0 and then look back into this circuit, I'll find the Thevenin resistance. That's going to be 36K in parallel with 68K. What region is this in? I have a fairly large base resistance. I guess that maybe I'm in the active region. Let's put the model in. Here's my Thevenin equivalent circuit going to the base. Between the emitter and the base, I've got the turn-on voltage of 0.6. Between the emitter and the collector, I've got a current source of beta FIB or 50 IB. Then I've got my emitter resistor, and then I got my resistor down here in the collector. And the value has been specified as 43K. This current is IB, this is 50 IB, so this is 51 IB. That's the emitter current. If I go around the loop this way, I just have one equation with I sub B in it. Let's do that. The rise in voltage is 10. The drop is 43K times 51 IB plus 0.6, and then plus 23.54K times I sub B plus 6.54. That's this equation. And solve for I sub B. It's going to be 10 minus 0.6 minus 6.54 divided by 51 times 43K plus 23.54K. And that's 1.29 microamps. That is greater than or equal to 0. So it's one of our checks. The collector current is beta FIB, so that's going to be 50 times this, or 64.5 microamps. And lastly, solving for the emitter collector voltage, which is what we've been asked to solve for. We also need to check that this is greater than or equal to the saturation voltage. Let's take this node voltage and subtract this node voltage. This node voltage, with the current going this way, is going to be minus 43K times 51 I sub B plus 10. The other node is going to be 50 IB times 33K. The difference of those two would be the emitter collector voltage. Plugging in the value of I sub B, I get 5.04 volts. That's greater than or equal to 0.2, so it checks. Part B, we're going to decrease the value of R sub E from 43K to 3.3K. Let's go back to the previous page. Take a look at this equation right here for I sub B. So make this resistor smaller. We're going to make the denominator smaller. That's going to make I sub B bigger. That might put us into the saturation region. So let's guess that. I'll take my active region model out and then put in the saturation model. So in the emitter and the base, I've got a turn-on voltage of 0.6, but now I've got the emitter collector voltage equal to the saturation voltage of 0.2. And then change the value of R sub E to 3.3K. A lot of ways you could analyze this. Maybe you could go back and use one of the techniques from ECE301. In Chapter 3 on pages 35 to 36, we had a mesh equation inspection technique. And the way you use that is to pick mesh currents in a clockwise direction. Call this I1 and I2. And then we're going to have a 2 by 2 matrix. What's going to go in row 1, column 1 is all of the resistances in mesh 1. It'll be the sum of these two, which is 56.54K. Between meshes 1 and 2, I've got a 33K resistor. It's going to be minus that value. And then if you go around the mesh counterclockwise, record all the drops you see. So minus 0.2 plus 0.6 plus 6.54 would be what goes in the left-hand side of the equation. Then we're going to multiply these two by the mesh currents I1 and I2. Same for mesh 2. Around the mesh, add up all the resistances. Now it's going to go in row 2, column 2. So 33K plus 3.3K is 36.3K. What's between meshes 1 and 2 is 33K, so we're going to subtract that. And then go around the mesh counterclockwise and record all the drops. Minus 10 plus 0.2 goes on the left-hand side of the equation. This turns out to be 6.94, and this is minus 9.8. You could solve for I1 and I2 using Kramer's rule. Or I just used my calculator, which could do a 2 by 2 matrix, and I just put the entries in and found that I1 was minus 74.19 microamps, and I2 was minus 337.4 microamps. The current I sub B is the negative of I1. That's going to be a plus 74.19 microamps. That's greater than or equal to 0. And the current I sub C is the current in this branch of the circuit, and that's going to be I1, which agrees with it, minus I2, which disagrees with it. The difference of those two is the collector current. is a plus 263 microamps, and that's greater than or equal to 0. The emitter collector voltage is 0.2 because that's part of our model. Lastly, we need to check the ratio of IC to IB. 263 micro over 74.19 micro is 3.5, and that's less than the beta F of 50. We are in saturation. In the last part of the problem, we're asked to solve for the value of R sub E, which would put us at the edge of saturation. We'll leave our saturation model in, but we're going to label the collector current now as beta FIB, or 50 I sub B. That's our edge model. I've got IB here, 50 IB here, 51 IB here. I want to be able to solve for this. I'm going to go around the loops. I've got 2 loops here. Let me go around this loop over here. I got voltage sources and just I sub B in it. 0.6 volts plus 23.54 K times I sub B plus 6.54. And then I've got, I come back around this way. I've got a minus 50 I sub B times 33K, and then minus 0.2 is back where I started. Adding up all the drops and setting that equal to 0. This is one way of doing Kirchhoff's voltage law. Putting the 0.6, the 6.54, and the minus 0.2 together, it's 6.94. I want to put this on the other side of the equation, so I'm going to get a minus 23.54 K times I sub B. This will be a plus 50 times 33K. And you multiply this out, you get 1.62646 megohms. I can solve for I sub B. It's going to be 6.94 divided by 1.62646 times 10 to the 6, and that's 4.267 microamps. And we need to check that that's greater than or equal to 0, so that's good. I need one more equation to solve for R sub B. I've got a loop here. I could go around this way. I go around the loop this way. I'll take this outer loop. The rise in voltage of 10 equals the drops of 51 IB times R sub B plus 0.6 plus IB times 23.54 K plus 6.54. And that's this equation right over here. And the 0.6 on this side with a minus sign, the 6.54, that's 2.86. Pull out the I sub B. I got 51 times R sub B plus 23.54 K. I can solve for R sub B. It'll be 2.86 divided by I sub B minus 23.54 K, and then divided by 51. Plugging in the value here of 4.267 microamps, I get 12.68 K. This value is between the value we had for active and for saturation. This is supplemental problem 317.